Okay, in this video I'm going to talk about the quotient rule for arithmetic derivative and extending the arithmetic derivative to the rational numbers. So recall that the arithmetic derivative is a function from natural numbers to natural numbers that is defined by the two properties. First, that for any prime number p, we have d of p is equal to 1, and then the product rule, which is that the d of the, so let's write for any two natural numbers m and n, we have d of the product m multiplied by n is equal to d of m multiplied by n plus m multiplied by d of n. So similar to the product rule for regular derivative of functions in mathematical analysis. So in one of the previous videos I showed that this derivative, this arithmetic derivative, can be extended from natural numbers to all integer numbers. So basically to 0 and to negative numbers. So now I will show that it's possible to extend it to the rational numbers as well. So, but first I'm going to show that the regular quotient rule that holds for regular derivative of functions in mathematical analysis, it holds also for the arithmetic derivative. So the product rule actually implies the quotient rule. So how so the quotient rule is okay, so let's derive it first, then I will give the statement. So basically we write that so let's say that we took two integer numbers m and n such that so these are integer numbers such that m over n is also basically m is divisible by n. So m is divisible by n. So then m over n is also an integer. So then we can write that d of m over n multiplied by n. So on the one hand, this is exactly equal to d of m, right? Because this argument is equal to m. On the other hand, we can, since both of these numbers are integer, we can use the product rule and write this, that this is equal to d of n over m over n multiplied by n plus m over n multiplied by d over n, right? So now we look at this and this, and we basically extract this value d of m over n. So we express it in terms of everything else. So so this implies that d of m over n is equal to, so this minus this divided by n, right? So it's d of m minus m over n multiplied by d of n divided by n, right? So we express this, and now we can simplify this. So we move this n to the denominator, right? So we write that this is n squared in the denominator, and here it would be d of m multiplied by n minus m multiplied by d of n, right? So, and this is exactly the fact that this is equal to this is exactly the quotient rule, and it is similar to the derivative of like regular derivative of functions in mathematical analysis. So we have if we have two functions f and g, then the derivative of the of f over g would be f prime g minus f g prime over g squared. So this is exactly the quotient rule that we have here. So okay, so and we obtained it only from the product rule. We used only the product rule and nothing else here. But here we so this quotient rule, it holds for now. Like what we proved is that it holds when m over n is an integer, because d is defined only for the integer numbers, right? So now the idea basically is to extend this function, like the arithmetic derivative, to the rational numbers using this quotient rule. So we basically assume that, not assume, but we define it for any m and n, regardless if m is divisible by n. So like so for any rational number q, it is represented as like by definition, if it's rational, it is represented as so let's say there exists m and n integers such that q is equal to m over n, right? This is basically the definition of a rational number, and we define, so d of q, we define it, so by definition, as d of m over n, which is equal to this, d of m n minus m d of n over n squared. So here in this, like this is more like in brackets, so I mean we can remove it basically, because q is equal to m over n, so this is not by definition, but this is the definition. Yeah, so now we need to prove the correctness of this definition. So the correctness means that first, like the rational number is not uniquely represented in this way, right? So it could be like it is equal to, basically we can multiply both numerator and denominator by the same number, so it's equal to mk over nk. And where is the guarantee that when we use these two numbers instead of m and n, this would give us the same result? So we need to prove this. And another thing that we need to prove is that the resulting function would still, for the resulting function for all rational numbers, the product rule would still hold. So that's the main thing, because by what we mean by extending the arithmetic derivative is not just to extend it, it's not just to define it to something and that's it, but to define it so that the product rule would still hold for all rational numbers. That's kind of the whole point of extension. So okay, so let's first prove that if we take this, so if we multiply both numerator and denominator by the same number k, then the value of d of q would be the same. So basically we need to prove that d of m over n is equal to d of defined like this, right? Would be equal to d of mk over nk. Okay, so let's rewrite both of them. So we expand this as d. No, I think it's better to start. But yeah, well, basically we'll start from here and we arrived at this. So d of mk over nk. This is equal to d of mkn minus mkt of n k here over n squared k squared, right? So now we expand both of this, d of mk and d of nk. So we write that this is d of mk plus md of k multiplied by nk minus mk d of nk plus n d of k over n squared k squared. And now so basically we see that one of the k's it's just cancel everywhere, so k, or not here, so k and k, so this cancel each other, and then we have so then then we notice that this term d of k multiplied by m multiplied by n, right? And here it's d of k multiplied by n multiplied by m. So this is the same term. So but here it's with plus, with the sign plus, and here it's with minus. So this term cancels with this term. Yeah. And so what remains is only these two terms. So d of m kn minus m k d of n, right? Well, to write them in the same order, let's write it even like this, k. Yeah. So over n squared k. So now k cancel each other, and what we have is d of m n minus m d of n over n squared. And by definition this is d of m over n. So So this is also by definition. So so basically we proved that this is equal to this. So so this equality is proven. This equality is proven, and the question mark we can remove it. So this proves the correctness of the definition. Just the correctness of the definition. So that if regardless of which representation of the rational number we pick, we would always get the same number when we define it this way. So so that proves the correctness, and now we need to prove that the product rule still holds. So the product rule for rational numbers. So basically we take two rational numbers q1 and q2. For them there exists like m1 and 1, m2 and 2, such that q1 is equal to m1 over n1 and q2 is equal to m2 over n2. And what we need to prove is that d of q1 q2 is equal, I put the question mark, we need to prove this, that is equal to d of q1 multiplied by q2 plus q1 multiplied by d of q2. So we need to prove that that this holds. This is the product rule for rational numbers. So basically let's expand. So we start from the left hand side and we will arrive at the right hand side. So d of q1 q2 is equal to d of m1 over n1 multiplied by m2 over n2. And so now this is m1 multiplied by m2 over n1 multiplied by n2. So this by definition of the function d for rational numbers as we defined it is equal to d of m1 m2 n1 n2 minus m1 m2 d of, so I rewrite the quotient rule for this fraction of n1 n2 divided by n1 squared and 2 squared. So now we expand both of these using the product rule. We can apply the product rule because m1 and m2 are both integers, and for integers we know the product rule holds. So we need to prove the product rule for rational numbers, but we already know that it holds for integers. So d of m1 m2 plus m1 d of m2 n1 n2 minus m1 m2. So what we have is we expand here, so it's d of n1 n2 minus n1 d of n2 So this is equal to so what we need in the end, we need to get d of q1, right? D of q1 is expressed as d of m1 over n1, so it would be d of m1. So like I'm trying just to gather the same to gather the multipliers that we need. So we take d of m1, so this term, right? D of m1 multiplied by n1, and then everything else. So this is in brackets, and then we have m2 and n2. So m2 by n2. Then we have minus, so the second term I would leave it for now. Then we have minus, I take m1 and d of n1, so this term. So this term would be minus m1 multiplied by d of n1, right? So this is brackets, and everything else is m2 multiplied by n2, so m2 and n2. And we notice that this multiplier is exactly equal as this multiplier. This is important. So this is in brackets, or like that's not right, square brackets, just regular brackets. And now we have here plus, so this is all in the numerator. In the denominator is n1 squared and 2 squared. And here we have, so we have remaining this term and this term. So for this term we take d of m2 multiplied by n2 and everything else is m1 multiplied by n1, right? Minus what? Okay, here we need to have plus, not minus, because it's a product rule for this. It's plus. So minus we have so m2 multiplied by d of n2, m2 d of n2 multiplied by m1 and n1, m1 and n1, and large bracket. And again we see that this multiplier and this are the same, so we can move it to outside of the brackets. So this can be rewritten as, so we write so in the first brackets, these brackets, so we move the same the common multiplier outside of the brackets, so we write m2 n2, here d of m1 n1 minus m1 d of n1 plus here the common multiplier, we move it outside of the brackets, and in brackets we have d of m2 n2 minus m2 d of n2. And in the denominator it's the same thing, n1 squared n2 squared. So now we notice that so this is equal to d of m1 over n1, right, by definition, which is also d of q1. and this is equal to d of m2 over n2. Oh no, not this, because no, excuse me, we need also to divide by n1 squared, so this one, so this, not just the numerator, but numerator with one of the multipliers in the denominator, and here like this over n2 squared, so this would be equal to this, which is d of q2. So in total we have the whole fraction. Let's write it below. So this is equal to m2 and 2 multiplied by d of m1 over n1 yeah, like let's write multiplied by n1 squared, so that to keep for now the denominator n1 squared and 2 squared, right, plus m1 n1 multiplied by d of m2 over n2 multiplied by n2 squared. Yeah, so now we just gather all the multipliers. So so we cancel one of everything. So n1, n2, n1, n2, n1, n2. So we cancelled. We divided both numerator and denominator by n1 and 2. So what remains is m2 over d of, this is d of q1 basically, by n1 plus m1 d of q2, this is d of q2, multiplied by n2, this is all divided by n1 and 2. So this is equal to, so now we write it separately. So d of q1, what remains here is n1 and 2, m2 and 1, plus m1 and 2, over n1 and 2, multiplied by d of q2, right? So now n1 and 1 and 2 and 2 cancel each other. What remains is d of q1 multiplied by m2 over n2 plus m1 over n1 multiplied by d of q2. So now we notice that this is exactly q2 and this is exactly q1. So in total we have d of q1 multiplied by q2 plus q1 multiplied of d of q2. Yeah, and this is exactly what we needed. So yeah, it's funny that I write the scale is larger and larger when I write the lines below. So yeah, so we see that what we obtained here, so this is exactly what we needed to obtain. So this is the product rule for q1 and q2. So what we needed here is the is this equality. So the d of, so we started from d of q1, q2, and we arrived here at this. So this is the, when we look at the beginning and end, this is exactly the product rule for q1 and q2. This one that we needed to prove. So basically this concludes the, so this concludes the proof of the product rule for any rational numbers. So it shows that our extension of the arithmetic derivative to the rational numbers defined above, it preserves the product rule. Like the product rule still holds for this extension. So now I think it would be useful to show a couple of examples for to calculate the arithmetic derivative for some rational numbers. So let's calculate d of 1/2, so 1/2. So by definition this is d of 1 multiplied by 2 minus d of 1 multiplied by d of 2 over 2 squared, right? So 2 squared is 4, so d of 1 is equal to 0. This is a well-known property, I proved it in the previous video. So d of 2 is equal to 1 because 2 is a prime number. So what we have is here basically 0, 0 minus 1, right? So this is minus 1/4. Yeah, so this is the answer for what is d of 1/2. Notice that it is a negative number. So it's not integer, which is natural, but in this particular case it's also a negative number, despite the fact that the argument is positive. So and then let's calculate d of 2/5. So this would be d of 2 multiplied by 5 minus 2 multiplied by d of 5 over 5 squared. So 5 squared is 25, and here we have d of 2 is equal to 1 because 2 is a prime number. D of 5 is also equal to 1 because 5 is also a prime number. So in total what we have is 5. The first term is 5 minus 2, right? So this is 5 minus 2 is 3, so 3 over 25, and this is equal to 0.12, right? Because if we multiplied both numerator and denominator by 4, we would get 12 over 100. 12 over 100 is exactly 0.12. So yeah, so we see that d of 2/5 is also it's also not integer naturally, and we can calculate it. So yeah, so this way we can calculate the arithmetic derivative of any rational number. Yeah, so that's it for this video.